Andres, it says hi on the bottom. Beautiful. Okay, you're good. Wait. Keep go back. All right. So are we? Would we like to start? Andres is going to need the whole thing. So
I might be okay actually.
think so?
Yeah.
Well, I want to start it.
We can wait a little bit.
Sure. We're recording right now. Did I turn on this?
What is the sound of one man chewing?
That's right. This is the way he eats his pizza. Oh, we're still on mute.
Okay.
I want to get things going.
Yeah, I don't know. Yeah, 2 more people.
Good. Make sure you kill all your sound.
So on the Hangout, I have to mute.
All right. Kill your sound. All right, good. So it's still going. That's not me, man.
That's technical. That's the technical
All right, welcome everyone.
So I have my volume on.
You have your microphone on?
Yeah, microphone muted.
How about now? I think we're good.
Okay. Yeah, that's fine.
Right, now, welcome everybody to our second idea talk of the fall 2018 term. Today we're welcoming Andrés Vargas for a return visit, an update on his shape signature work. It's advanced quite a bit since the last time he was there. Just a couple reminders, we are streaming and recording live, so you're welcome to ask questions at the end. Andrés has a lot of material that he'd like to storm through, so if we could, unless there's some big issue with what's on there, let's try to keep your questions until the end, and he's planned for some Q&A at the end.
Yeah, I have like slides that have like question slides.
Okay.
Good like stopping points.
So without further ado, thank you very much, Andrés. Take it away.
All right. Hello, everybody. As John said, I'm Andrés, and I'm in my 5th year of my PhD right now. And I'm going to be talking about some work that I've been developing over the past 2.5 years or so. It started with semiconductor manufacturing data, and it started with anomaly detection, but it mutated into a whole additional beast. So I'm going to start with what I did first, which is my work in anomaly detection, and then go into the beast that it became. So I'll start by giving a small background on semiconductor manufacturing. Then I'll talk about the structure of the data from the manufacturing plant that I initially was working with. Then I'll talk about the anomaly detection algorithm. I'll give some empirical results of the algorithm, give some room for questions, and then I'll go into the section that talks about why the algorithm works, and it provides some theoretical justification for some aspects of the algorithm that I didn't even realize when I was writing the algorithm. It just kind of was an explanation that came about when I thought about underlying causes. Then I'll give simulation results for those theoretical considerations, and then I'll give conclusions of future work. So first, to give some background on semiconductor manufacturing. So semiconductor manufacturing, it's the goal is to transform these blank silicon wafers into electronically functional computer chips. And that's done by depositing special material on the wafer surface. And that's done inside these chambers, which we call tools. So on the left side, you have a corridor of chambers in a semiconductor manufacturing plant. And if you look at just one of those tools, as the picture in the middle does, and then go within that tool, you have this diagram here, which shows what happens as a wafer has that material deposit on it. And so it's on this axle. This is a cross-sectional view. So it's on this axle, and as on the axle, it's spinning, and the material is being dropped onto the center of the circle in which it's spinning. And due to the angular momentum, it's just shot across all parts of the wafer. And you do that over and over again with different types of material until eventually you have an end product that you want to distribute. And so the goal is that you want to have the best end product possible. And you want to avoid faults in that deposition process and catch them as soon as possible. Because every time you manufacture a bad wafer, it's going to cost you money at the end. And the longer that wafer, if it's already bad, goes through the process, that's energy that could be spent on scrapping that wafer and starting over with the wafer that's actually going to be used. So now we have a lot of data that was collected during this this process inside an actual semiconductor manufacturing plant, and I'm thinking about the data as a 4-dimensional array. And one of the dimensions gives the tool that a wafer is manufactured in. Another dimension is the sensor, because you have various sensors being collected within that tool. And then you have another dimension being the step, because as the wafer goes through the tool, recipe is performed, and that recipe proceeds via a sequence of steps. And the final 4th dimension is the wafer itself, and that dimension is actually ordered in time, because you have this batch process, each element of the batch being a wafer. And as the wafers go through, time is passing. So the last that wafer dimension is ordered in time, but the other dimensions are not. And so each element of this array, and it's an array, not a tensor, because the elements are not numbers. It's the elements are actually time series, univariate time series. And so each element is univariate time series, and the time is just whatever time was measured relative to that step. And the sensor is whatever sensor dimension you have to be in, right? So if you slice the array by fixing the temperature, you can actually visualize it in this way that I do on the picture on the right. And so each plot in this lattice is a tool, and the y-axis is the temperature, and the horizontal axis is the time elapsed. And the data is colored by step, and all the wafers are actually superimposed on, all the wafers passing through each tool are superimposed together. You just can't really tell them apart because there's not enough resolution. But there's actually hundreds of wafers that we have data for in each of these plots. Okay. So we have that. If we think about the data in that way, and we zoom in on one of the tools that I showed before, okay, remember, our ultimate goal is that it's to detect anomalies, right? So we zoom in on one of those tools, and we zoom in on one step, look at the data for just one wafer. We see that it follows this oscillatory pattern. And there's a reason for that, which I'll go into later. But for now, all I really want you to think about is that this happens for every single step in every single sensor and every single wafer and every single tool can be modeled by this oscillator. And as I said, there's a theoretical reason for that. But for now, it's just take it to be true. And so that means that if we fit parameters to these oscillators, we can save the parameters and use them as a summary statistic for the data in each tool, sensor, step, wafer, quadruple. So this is just showing that so this one takes 2 wafers, this one took 1 wafer, this one takes 2 wafers from the same step, this one takes like a lot of wafers from the same step, but all of them follow this similar shape. So there's certain times when the shape in each step will be a special case of this general damped linearly driven oscillator. And we can account for that in the algorithm. We'll come back to that later on. For now, assume that it's the most general case, figure 1. which is a damped harmonic oscillator with a linear driving force. And so, like I said, we want to fit a curve to that object for each tool sensor step wafer quadruple in our data. And we do that by using a constrained nonlinear Bayesian regression. So what we're doing is we're putting a prior on the vector of parameters that defines that oscillator. And then we're decomposing the joint probability into the product of the likelihood of the prior. And so by putting a prior on the parameters and then calculating the likelihood, maximizing that product, maximizing the product of the likelihood and the prior, we're actually learning the shape signature parameters while regularizing in the case where there's not enough data. The prior served as a regularization term if you don't have enough data. And so there's some math here. This is essentially just minimizing the negative log likelihood of the likelihood times the prior. The negative log of the likelihood times the prior, which is the same thing as maximizing the likelihood times the prior. And we call the optimal solution to this optimization problem the shape signature of the wafer. And on the right, you can see the end product of this thing if you do it for a single lot of wafers, right? Each lot has a number of wafers. So processing the wafers in lots like this and feeding them into the optimization program, that allows for learning of the prior. And so when you're done, you have estimates of these oscillators, right? So are there any questions up to now? Okay, so to summarize what we've done so far is if you look back at the tensor representation, each element of this tensor used to be a univariate time series, but now we've represented it as a shape signature. And so, that signature is defined by 7 parameters, as it were. So we now have 7 parameters assigned to each element of this 4-dimensional array. And now, so what that does is it compresses the data, first of all, right? Well, what used to be a long time series, hundreds of observations, is now 7 parameters, so that helps in that sense. Secondly, we've captured physically meaningful nonlinear behavior of the data. For instance, the damping coefficient parameter, right? That encodes how fast your data settles to the target set point. Like you would never be able to know that just from the raw data. And frequency as well tells you how quickly it's oscillating. In general, you'd like to minimize. You'd like for it not to oscillate too much. And so these parameters are encoding important information from a process engineering point of view. But now we want to use these curves, these parameters of these curves for anomaly detection. So we're going to want to assign an anomaly score to each tool sensor step wafer quadruple in this array as a function of its corresponding shape signature. But the first thing we need to do before we get there is to define an anomaly scoring function. And anomaly scoring functions, there's nothing really telling you how to choose one a priori. You kind of, in practice, want to choose one that's meaningful from the domain that you're working with. And logical as well. You don't want to just choose like the anomaly scoring function being like x squared, where x is your data point. It doesn't make any sense. So this is how we're going to think about the anomaly scoring function. So the company that we were working with gave us 2 very important requirements for the anomaly score. The first of which is that it penalizes noisy data. And the second is that it penalizes deviation from the normal model of chamber operation. So with those 2 requirements in mind, consider the function anom of w is the wafer, equal to, this is the negative log of the likelihood times the prior. And you just separated it into this sum of the negative logs just by the properties of the logarithm, right? And so the first term, this negative ln probability of z given s and sigma, so z is the data now, that's the likelihood, okay? So that encodes the quality of the fit to the data. It encodes how much noise there is in that particular wafer. And the second term is the negative log prior, and that encodes the degree of adherence to the prior distribution. Okay, so that means now that if we somehow encode the normal model of operation into the prior, that this anom w function will meet the requirements. So how do we encode normal model of operation into the prior. So I propose this way of doing it, where you assume the set of data that occurred at the very beginning of data collection, you assume that to be normal. And really you have nothing else to work off of, right? Because we don't have labels in this. We don't have labels as to what's normal and what's not. So the best we can do is really just to take something at the beginning and assume that's normal and work from there. So if we do that, and we set L to be a set of contiguous and timed wafers at the beginning of the data collection period, and now we plug that lot of wafers. Remember, before the optimization algorithm operated on lots of wafers. But now, if instead of processing a single lot, we instead consider a lot to be just however many wafers we chose at the beginning of time, then if we solve the optimization problem, okay, we'll get, and we save the parameters of the prior and the standard deviation of the error, then we can consider that our normal model of chamber operation. Does anybody have questions on that logic? Yeah.
So this may be some really obvious question, it might be, but why negative log?
Okay, so that's a good question. So you agree that this does address these two requirements, right? You agree with that?
I think so, yeah.
Okay. So if you agree with that, then the question is, why choose this instead of some other function? And the reason is because this function is actually the objective function of the optimization problem we're solving. So we can actually compute it for free at the end of the optimization procedure. So it comes easily. I can go in, it goes into a little more in a I think, few slides. No, it doesn't. So I'll go into it now. So yeah, so if you look at the optimization problem here, this is exactly this. Right? The objective function is as this. The only difference is that now this sigma star, US star, and sigma S star, those are normal model parameters. Whereas here they're being optimized over. So after suppose you've learned the normal model, and now you're talking about you want to assign an anomaly score to a wafer that comes later in time. You can solve this problem for the wafer, and then substitute in this sigma squared, sigma star, US star, sigma S star, into the objective function upon termination of the optimization procedure. And you have an anomaly score for that wafer for free.
Okay, but why log specifically? You don't have to P yourself or some other.
Well, okay, so first of all, P, the actual probability is not available because you have a continuous probability distribution. You have a density. So that even if you didn't include the log to win it, there would be no way of getting the actual probability. But additionally, the log helps because the log is going to scrunch that density down. Because densities can be presumably huge. Because there's no restriction between 0 and 1 as long as it integrates to 1, right?
Right.
So you can have these enormous values in the probability density that may become numerically infinite. Right? But if you apply a log to them, then it scrunches together so it doesn't blow up as high.
Because you're approaching one.
Yeah, because the log function in general, it takes a large value and just scrunches it. That's one of the properties of the logarithm function. So if you have a really large value in this probability density, well, you take the log of it, and then it's not as big anymore.
It's optimization.
Yeah. So we don't explicitly include the logarithm in terms of the optimization problem because we're assuming normality. So when you take the log of a normal distribution, the e just goes away. You end up getting something simple. So analytically, it helps a lot.
I've been putting around with different probability normalizations, but.
Sure, yeah.
A quick question, Andres. Could you remind me again where the normal model comes from? Does it come from the data itself, or is it something that they know?
The normal model comes from running this algorithm.
Oh, so you use the optimization.
Yeah.
So in that case, is there ever any drift in there where you have to update the model?
Yeah, so we don't account for drift right now. This is
something that you.
Yeah, it's something that's going to come hopefully later on. But there is drift in the process for sure. So this is a step-by-step procedure how to compute anomaly scores given what I've just described. And so it's pretty much what I just said to you. You assume the normal model has been learned on the initial set of wafers, and given a lot of wafers, you compute the shape signatures for those wafers using the optimization algorithm, and then the anomaly score of SM star, which is the shape signature of wafer M, is just equal to the negative log likelihood minus the log prior, and you just substitute in the normal model parameters for the parameters of the distribution.
I have a quick question. I guess when I think of anomaly scores, I think of some sort of like reconstruction error. Is that a useful metaphor for what's going on here, or is this like a different type of anomaly detection?
Reconstruction. I think a better way, not for this, I think a better way of thinking of this is just distance, Mahalanobis distance from the prior.
And so is there a guarantee that this anomaly score is bounded below by like 0 or something?
No,
Okay.
there's no guarantee. In fact, we have negative anomaly scores. Doesn't present a problem though, because we just consider them as on the scale less than any anomaly score that's less negative. So if we repeat this for all lots, then we can get an anomaly score for every single wafer, and every single sensor, and every single step, and every single tool in our data. So now, coming back to something I mentioned before, you have instances in your data where it may not be like the most parsimonious decision to model it using the most general model, and it might be a special case of that model. So, for instance, on the left here, this is 3 wafers, each one color, different colors, so it doesn't really look like an oscillating function would be appropriate for that. Something exponential might be better. And in the case on the right, it's really unclear as to what you would set, in particular, the frequency to. Right? There's all this noise, and algorithms are notoriously prone to aliasing in the frequency domain unless you take some cautionary measures. So in that case, I would argue that I would prefer for the algorithm to fit a constant function there. So we're going to use 2 levels of regularization for model selection. The first level is going to be using the Bayesian information criterion, and the second level is going to be using a majority voting mechanism. So for the Bayesian information criterion, it's defined as k natural log of n minus 2 natural log of the likelihood of n. And m is your model, k is the parameters in the model, n is the number of observations, and as I said, L is the likelihood. So it's essentially, it's penalizing you for having more parameters, and it's encouraging you to have a large likelihood. And we're going to take the minimum choice for that function. We're going to take the model that minimizes that function out of, for us, these 6. And so that's for the first level of model selection. But BIC, although it's both empirically and theoretically justified, and it's been used for a long time in statistics, it's not perfect. And we can actually make it better by using domain knowledge. So, for instance, these 2 cases, right? In these 2 cases, in the left case, BIC chose this exponential function, which may not be the best choice because you have these pretty obvious oscillations in the data that are better modeled with a more complicated function. So with no model selection, you were actually better off with no BIC, and similarly in the right case. So how can you add an additional level of checking to make sure the BIC is fine? And so the key realization here is just that tools that use the same recipe should have the same data model for like sensor step pairs. So meaning that if you have the same recipe being performed on 2 different tools, and you take the same step for each of those tools, and you take the same sensor output, then there should be the same hypothesis set of functions, right? Like presumably that shouldn't be different. So you can impose that by, after having the BIC decide the model choice for each tool, you then take the majority vote and assign that to all the tools. To impose that physically plausible constraint, right? And so when we do this, it actually ends up going back to the example I gave before. It actually fixes the problem. So before, with no model, with no BIC, it chose the linear, the exponential thing. But then when you impose the majority vote, you end up seeing. I show here explicitly what each tool, what BIC decided for each tool, and we see that for all tools except for tool 3, BIC decided damped linearly driven oscillator was the best model. So damped linearly driven is clearly the majority vote. So we then reset tool 3 to majority vote, and we see that it's able to do a good job of fitting the data. Fits the data in the way we would like it to. An example that shows the whole full circle thing of the 2 steps is this one. So the bottom picture here is before BIC or majority vote. So in the bottom picture, tool 3 without any model selection is just grossly overfitted, right? It's just the fits make no sense, and that's because we were trying to fit a damped linearly driven oscillator to data that had way too few data points. With BIC, you end up choosing a damped constantly driven oscillator for tool 3, which from a visual perspective does a good job of modeling the data. But if you now are going to fit subsequent wafers of data with the same model, you might be susceptible to variance because it doesn't look like there's going to be any oscillations in that data, but the damped constantly driven oscillator has oscillations, an oscillatory term built into it, namely frequency. Take the majority vote, it ends up choosing linear exponential, and that's what we would like. So that's the 2 levels of model selection. Are there any questions on the model selection? Yeah.
I don't know much about the BIC, but is there any reason why you wouldn't use like a p-value instead to calculate the measure of bestness?
Like a p-value on the likelihood?
Well, no, just like how well it fit, right? Like, because obviously for like that one thing that like the damped oscillator fit way better than like what it actually picked.
So you're talking about a p-value on the sum of the squared residuals and computing like. So
you could use like like a concordancy score or any like other way.
Okay, so suppose you take the sum of the squared residuals and you apply and you look at it as a chi-square random variable, right? And you do a p-value for that.
You could do it that way, or you could do it another way. Yeah.
Right. So the problem with that is that it doesn't account for the prior.
Okay.
Right, because the thing you're maximizing is not just the likelihood here; it's the likelihood times the prior. So in that sense, I wouldn't really know how to approach the p-value thing using it that way. But yeah, so that's why. So that ends the description of the algorithm, and from an implementation standpoint. Just the whole thing I've been doing with this mouthful of tool sensor step wafer, you're naturally going to wonder if you can speed things up by doing it parallel. And as it turns out, you can, and it's embarrassingly parallel, meaning that the optimization procedure for each lot of wafers is independent of the optimization procedure for any other lot of wafers. So we've used a very nicely structured server that we have access to, and distributed computing capabilities of R to greatly reduce algorithm runtime. And the algorithm uses block coordinate descent. Specifically, one of the blocks is for the nonlinear shape signature optimization problem, and the other block is for learning the parameters of the prior. So you go back and forth, eventually converting to a stable solution. The shape signature part does not have an analytical solution, so you need to use an iterative procedure for that. I use modified Newton descent. And the good thing about modified Newton descent, the reason I chose it is because our problem has low dimensionality, right? Just trying to learn 7 parameters. So that means that we can actually feed the algorithm, if it gives us the opportunity, the analytical estimate. So I do that to improve performance, and learning the parameters of the prior after each iteration actually has an analytical solution. So no iteration needed for that. Okay, so any questions on that?
Just as do you often get like ties in the votes?
Yeah, so for ties, I choose the most complex model because in the way I reasoned through it was that this is not a predictive test. We're not trying to predict how future data is going to behave based on the model we learn. It's just an explanatory test. We want to summarize the data as best we can. So from that perspective, I think the risk of being too conservative is more than the risk of being a little bit overly conservative. So this is a case study on. This is a case study showing how one might use this. First of all, on the triple level. So a triple is you fix a tool, sensor, and step, and you monitor the wafers over time. And you can look for points in time where the anomaly score spikes up. So here we look at this one. So that might hint to a process engineer that something's going wrong there. So if we zoom in on that spike point, and we look at how the shape signatures are behaving during the spike point, we see that this guy here, which visually looks different, is the one that received that high anomaly score. So I guess essentially this is just saying that the anomaly score does a good job of detecting something, which you would expect by construction. But it's just showing how you can monitor it over time with heat maps. At a much higher level, or actually no, not yet, at a lower level, you can actually take the gradient of the anomaly score at a spike point, for instance, and the largest elements in magnitude of that gradient are going to tell you what parameters of the oscillator or the shape signature are contributing most to the anomaly. So if we take the gradient at this spike point, we get this vector, and we see that the element corresponding to the C parameter, which is the slope, like without question trumps in magnitude all the other parameters. So what that means is that we can conclude that C is contributing to the anomaly, to the spike. So this is actually, it's not easy to see visually, right? If you were to look at this picture below and ask yourself, what is causing the high anomaly score or causing this bottom section to be different, you would think it was like the vertical shift. But as it turns out, it's actually the slope. And the reason the algorithm is able to know this is because in the initial fit, in learning the variance of the variances of the prior, it actually learns which parameters, like the scale on which each parameter is varying. So it knows that even though the Y shift in this case may have changed a lot visually, it learned to not pay much attention to shifts on that scale during the initial fit. But it learned to pay very close attention to shifts on a very tiny scale for the slope. So that's why this the element of the gradient corresponding to C is greater here, even though it's not visually apparent. So now on a much higher level, if we now plot just the anomaly scores, not the parameters, just the anomaly scores for each triple or for each double and each tool, right? So now we're looking at tool 3, and we're taking each combination of sensors, and we're monitoring the anomaly score over time. Time is now going in time is going in this direction, and so we can look on a very high level at points in time where you see many different anomaly scores spiking. And so in particular, I've directed you guys to this point here, which is it's pretty apparent that something's going on here, right? You have all these anomaly scores going from low to high for many different sensor step pairs. And so you can ask yourself, if you're like a process engineer, like looking at this on a screen on the factory floor, you can be like, all right, something's going on, and just investigate that further, right? So this is kind of like what I would think might be the use case of something like this. You can do this for any tool you want. Well, so before I get into some of the theoretical explanations, are there any questions of what I've talked about so far? Yeah.
Would there, I guess for the person, because there are a ton of tools and a ton of wafers and whatever, hopefully there would be a way that you could just make an algorithm to look at just maybe that matrix and find anomalies in the anomalies.
Yeah, no, exactly, that's true.
Yeah, so are you planning on doing anything like that?
Yeah, definitely, that's in future work, and it's just like one step away, right? At its simplest, you could set a threshold, or you could do like a statistical test and consider the anomaly scores to be a random variable, and then
or even just like clustering would be like super
Just
right?
classify the anomalies.
Say that again?
This is you can just try to classify the anomalies or something.
Yeah, but you don't. The thing is, you don't know what's anomalous a priori. That's not included in our data set. So that's what made this challenging problem. And a lot of times with anomaly detection in general, you don't know the true labels in practice. So that's what makes it like a tough data mining problem, tougher than some other ones.
Yeah, so maybe you could look at maybe like fold change or something like that, but like in between steps or time points or something like that. Yeah.
Yeah, it's in the future, especially if we're thinking about deploying something like this in a factory. But given my background, I'm at the moment I'm currently a lot more interested in explaining like why like this function is an appropriate fit, an appropriate data model or hypothesis set for each tool sensor step, wafer, triple or quadruple. And so the motivating question here is exactly what I just said, and it's not a coincidence. As a matter of fact, it arises from the underlying feedback control system. And so the questions to be asked are, can we model the system? And if so, can we analytically connect the system parameters to our fitted oscillators? And so we can try making some simplifying assumptions perhaps, but first, I know some people may not be familiar with feedback control, so I'm going to give a brief introduction. So feedback control as a study tries to control process variables as a function of control variables. And the process variables need to be kept at certain settings in order to make the manufacturing process like optimal. But you can't explicitly control them. You can only control the control variables, hence their name. So some examples, if you're talking about univariate control, so one variable as a function of another, temperature can be controlled as a function of power, and pressure can be controlled as a function of throttle value. So the big question in feedback control is how do we adjust the control variables such that the process variables reach the point where we would like them to be. So this can be done with a feedback controller, and a popular choice in industry is a PID controller, which stands for proportional integral derivative. Currently, about 45% of industrial control systems use PID controllers, and the general formula for it is just this right here. You're adjusting U of t, the control variable, as a function of the error, and the error is just the difference between the current value of the process variable and the value you would like it to take. And so the proportional term is directly multiplying by the error. The integral term is accounting for information that occurred in the past, errors in the past. And the derivative term is trying to essentially predict where the error is going to go forward in time, in the near future, by using the derivative. So now we would like to hopefully model this feedback control system as closely as possible and see if we can connect it to the oscillators. So in general, you can formulate a feedback control system as a set of blocks in a block diagram. One example might, so in the block diagram that I've given here, you have an input, you apply the controller to it, then the process happens, and then you have an output. So the controller is what I just described. So one example might be a PID controller. The process is something that exists in nature. Okay? We don't design it. It's just physical laws that dictate the relation between the input and the output. And the controller can be made as simple or as complex as the company would like. Simple ones are cheap and easy to tune, which probably explains why PID is still used even after so many years that it's been around. But if you make it complex, you can get high performance, but it's no longer cheap or easy to tune. Process, in practice, processes are very high order. For instance, General Electric has approximately a 300th order process. And they approximate it with a 30th order process, which is still huge. So we can settle for a low order approximation of the process, but how low are we willing to go before it starts just completely biasing our results? So these are some main questions that we have to ask ourselves if we want to model this feedback control system. And you can add more blocks to this, right? There's a control block, there's a process block. You can add blocks that account for disturbances. You can add blocks that account for all different types of things. And in practice, they have many more blocks than just a controller blocking the process block. The order of the entire system is an increasing function of the number of these blocks and the order of each block. And once you have all your blocks, you can actually derive a transfer function, which essentially encodes all the blocks together and gives you a single Laplace domain relationship between the input and the output, just a combination of all the blocks you have in your system. And the key point here, which is going to help us relate this to our oscillators, is that regardless of the order of the system, the output sensor data will behave similarly to data from a first or second order system, i.e. an oscillator. So below here, this is not actual data. These are actually things that I ran on Wolfram Alpha for equations that I know to be byproducts of high order systems, right? So this is a fifth order system on the left, and it looks as such. And if you just remove terms of that equation, such that it is now the output of a second order system, it looks very similar, right? It's still an oscillator with the oscillation just behaving differently. So that essentially shows why we might believe that regardless of the order of this process, which is presumably very large because this is an actual industrial plant, this explains why we still see oscillators occurring so ubiquitously. So to prove the concept, we can start from a very simple control system. GAT controller is what I chose, and we assume a first order process. And with a couple of other assumptions on initial conditions and the set point, which is the form of the target you want to reach, you can actually derive analytically our oscillator formula. So each function, so the parameters of the oscillator are now expressed as functions of the original control system parameters. So that's the forward operator. And so a natural question is going to be, can you do the inverse operator, right? Can you go from the oscillator to the control system? And is that relationship one-to-one? So I'll talk about that in a bit. But for now, in terms of the forward operator, you can sanity check that the derivations work by simulating this exact control system in MATLAB. And the simulations exactly match up with what we derived. So this is just like a sanity check to make sure that essentially that my math is right. And again, these same oscillators also appear in our data. At the top, we have the damped linearly driven case. In the middle, damped constantly driven case, which is a special case of damped linearly driven. And at the very bottom, we have a constant model, which is just another special case. So the conclusions of this inquiry into feedback control is that our damped linearly driven oscillators that we use as summary statistics for each element of our data array are actually gray box models in the sense that they are directly related to the parameters of a real physical and causal system. And so that means that since this algorithm detects anomalies as a function of those parameters, that these anomalies are functions of the underlying control system parameters. So if you know the control system, we can explain the anomalies exactly in terms of those control system parameters. Now, when it comes to the inverse operator, which is how you would in practice go back from the anomalies to the control system, I haven't done that for the actual semiconductor data because I have no idea what, well, I have a kind of an idea, but not really a good idea of what kind of control system generated that data. But I've analytically derived it for the simple assumed controller. So you can go back and forth, and it's one-to-one. So that means that we can in theory, we can simulate anomalies from MATLAB and then catch them using our algorithm and then go back in that way, right? The actual plant probably does not use the assumed control system. And generalizing the derivation to a more complex controller, it may be intractable. I haven't tried it yet, but I have a feeling it's intractable. Even so, the framework, I think, can still be used to gain insight into manufacturing system for design optimization. Like I've tried, like given the assumptions of like a PI controller and whatever else I assumed in the simple controller, I've taken the oscillators that I fitted to my data and gone back and like thought about what those parameters mean. Not really sure yet, but it's a work in progress. So I think, yeah, so I can actually, so from this whole feedback control, I guess, inquiry, we've realized that certain variables are coupled, specifically the control variables and the process variables. So now going back to our data, using these newfound insights, we can plot a three-dimensional oscillator, which is just plotting time on one axis and one of the variables that we know to be a process variable and another variable that we know to be one of the variables that's controlling that process, and just and take a look at what a three-dimensional coupled oscillator might look like. And so it looks like this.
That's awesome.
Yeah, it's just, yeah. So this is what happens when you couple them and you plot them. So it's this spiral. And the spiral, if you look at it this way, it's kind of, you can see the dampening occurring, right? From one side, from the right side to the left side. That's the dampening. And you would project this spiral onto the 2D plane formed by time in one of the variables. You would get exactly the shape signatures that we saw earlier in the presentation.
Could you cut it down to one, maybe one trace, one wafer? Yeah.
Sure. There's one.
So is the PID formalism, is that entirely deterministic? Or like, because your gray box model is a stochastic noise, but are you assuming the control system doesn't have any errors? Or?
Yeah. So there's two ways of thinking about it. One of them is, if you think about it deterministically, then you can think of the prior inner model as simply a construct that you're imposing in order to help you fit the model, in order to get the parameters, and forget about what that probability actually means. The other way of thinking about it is that if you assume that the underlying control parameters have a distribution, then that would imply that the function of those parameters that maps them to the oscillator parameters is also going to have a probability distribution. And I've tried to simulate that. I've actually simulated that with a Monte Carlo simulation, and so the parameters of the prior are probably not Gaussian exactly, but they probably are unimodal. That prior is probably unimodal. That's all I've been able to kind of discern up to now.
Do people do like stochastic PID ever?
Yeah, so stochastic system, what's it called? Stochastic system control is when you some parameters are unknown, you put probability distributions on them, and derive behavior of the systems probabilistically. So for instance, stability of a system, meaning if the oscillator dampens out to or diverges, that's determined by the zeros of the denominator of the transfer function. And so if you can get a probabilistic estimate of where those zeros lie, you can get a probabilistic estimate of how likely your thing is to be unstable. These are all things that I'm thinking of looking into.
So Andrés, the process control model, they know the form of the model, but they don't necessarily know coefficients at all times because it is a feedback control loop, right? But if at one instant you knew what those coefficients were, would you then be able to analytically derive your normal model from them?
Yes. You wouldn't need
right. That's
probability. You wouldn't need probability.
Right. That's by definition that is the normal model. This is the way that they.
Well, and that's if you assume the things that I assumed, right?
Yeah.
I think the answer is yes, if the parameterization of the real system fully reflects not only that.
It's just a resounding yes.
But it has to be the yes of everything. It has to be the yes of the whole system. It can't be simply the yes of the that you. How was that?
Hail.
It can't just be the parameters that you program into your controller. It has to be the whole reality of the system. And you may only have the parameters that you have in that system. You have to evaluate the system to actually discover the realized reality of the control plus the controller plus the physical environment to get the actual behavior of the system.
The controller may be known, right? The control parameters, but the process is like never known, right? But there's whole teams of engineers devoted to discovering.
I mean, what you're seeing here is the system settling as the feedback control adjusts, right? Over some short stretch of time.
Yeah, but this is including every aspect. I mean, this is including the behavior of the gas. This is including
Sure.
the interaction
physics
with the
don't know
wafer.
inside
This
it.
is the realized, the observed photo reality.
Well,
And that's why he has to do the norm, establish a norm based on what it's doing. From
Well, I mean, I just posed a hypothetical question because, even if you could, at any single instant in time, understand what those coefficients were in their equation, it's constantly changing as the feedback loop evolves over time.
No, not unless they explicitly change them, right? What's changing is just the value of the process variable and the control variable, but those parameters remain the same unless
The parameters of the equation don't change.
Yeah,
So that was my question then, to relate the parameters of that equation to the parameters that you get from the characterization that you're doing fitting.
Yeah, I mean, if they're the same and I've expressed those parameters of the equation as deterministic functions, then it wouldn't change. But then there's always noise in the data and stuff, so it's just, yeah, that might change the actual estimates.
I mean, in a sense, what you've got something similar to, I think, the circadian data here, except what's been put in at the beginning. So you're essentially, in some general fashion, fitting the curve to this data. But you also have prior information about how that data is actually being generated.
Yeah, so look, we have like a hunch, you know what I mean? Like we know.
You've got the feedback control model and things like that.
But you don't have the real one.
We don't have one.
You don't have the real one. You don't know.
No,
The real one's more complicated.
I understand that.
But there's another point though, is you do have parametric drift. Because the throttle valve gets clogged up and those parameters
Absolutely.
evolve, which is the whole point of this anomaly.
And that's why I said that, the thing is going to, it's going to evolve over time because the physical conditions are changing.
That's right, but it's not necessarily due to any
I'm just trying
intentional
to establish, some correspondence between the parameters of the feedback control system and the parameters that he's discovering in the data itself.
This is like your
I mean, it's there, right?
Yeah, that's
this is like your cruise control changing as.
You go up and down hills.
No, it's as your cruise control changing as your tires wear down. And your cruise control changing as you and you wax your car a little bit differently.
All right. So this is just my concluding slide. So for future work, I want to use Laplace prior and Laplace errors instead of the Gaussian prior, because sometimes you see things happening like you see on the top right, where in the absence of like enough data, one weird data point can really throw off the shape signature that you learned. You don't want that, right? You want to learn a shape signature that's in the absence of data, similar to your prior, and allow that data point to remain just noise on its own. And that noise will be captured into the likelihood term of the anomaly score. Right? You want this data point to contribute to the anomaly score only in the likelihood and having a high negative log likelihood, as opposed to contributing to the anomaly score by just throwing off this fit. So that can be done with the Laplace prior and Laplace errors. For anomaly detection, as we mentioned before, I would like to incorporate this into an anomaly detection framework where you actually can change the normal model of operation given enough anomalies back to back. Then that can be developed as a novel framework or plugged into one that already exists. And from a feedback control, I would like to experiment with higher order controllers and processes. At dead time is something that's definitely there physically. It just means that there's a lag between what the controller does and there's a lag between how you adjust the control variable and how the controller responds to that. Like there's a lag time between that. And then multivariate controllers, which account for interactions between different sensors, because more than likely that is definitely going on. Although I'm pretty, when we were working for the company, they did say that they were using a PID control loop, but probably in some sort of coupled way. So I think it'd be really cool if by the time I'm done here, I can somehow figure out a way, like tell them what they were using. Yeah, figure out what kind of controller they were using. Yeah. Yeah, that's it. Thank you.
All right. So what other kinds of systems could you apply it to? Like biological systems or
Yeah,
something?
I mean, biological systems, people model them with feedback control systems as well. So,
Wouldn't a Laplace prior just make your parameters more likely to be sparse and not directly impact how robust to noise your fit is?
yeah, only if you assume the mean of the prior is 0. If not, it's going to bias them toward, it's going to take the median.
Yeah.
You use a Laplace on the errors, but not on the parameters.
Yeah, so Laplace on the errors would also help. So yeah, there's 2 levels, right? A Laplace on the errors would avoid something happening like this on the top right. A Laplace on the prior would avoid if the actual state signatures themselves are like all in one spot and then one is like way up here. It wouldn't account for that one. It would still take the median and stay here, which is what you want, right? If you learn a safe signature, a bunch of them they're here in the normal model, and one of them happens to be up here, you don't really want the mean of the prior to be here. You want it to stay where everything else is. So it's just it's doing the same thing as the error Laplace prior does, just at a higher level of abstraction, because now you're dealing with functions as opposed to actual raw data points.
So what do you see as the relationship between this and information theory, like information
I'm usually able to predict what you're going to say, but
From an entropy point of view, I think your objective function could be entropy-wise as well. I don't have it memorized right now, but does anybody know how the entropy function is related to the likelihood, right?
Well, it's all logs, so
Yeah.
you already got logs.
I knew this when I was taking input theory, but
where's Shannon when you
it's
need him?
not, yeah. it's not in the
It
back of my mind.
seems like they're, at least conceptually.
They are, yeah, and I mean, and that's why you use the entropy loss in things like deep learning, right? So if you wanted to formulate it in terms of entropy, then you would, instead of using your objective function being the joint probability, or instead of your anomaly scoring function being the joint probability, your anomaly scoring function would be just the entropy function. I haven't tried that.
Yeah, so like if you were like viewing your anomaly detection as like a compression, then the anomalies would be the points that aren't compressed very well. And so you can think about that as like neutral information, I guess, because if you use like a data processing quality, and then that would give you another way of getting an anomaly score, I think.
Awesome.
We had a question.
You ever find that your model?
Well, so yeah, so there's times when that procedure pick things that I would prefer for not to. And actually, this picture here shows one example of that. So after the 2 levels of model selection, this is one example of somewhere in our data when it still chose a definitely driven oscillator, where I would have preferred for it to have chosen a constant one. So it still sometimes doesn't work even with the 2 levels of model selection. So it can either be argued as not working or just not, yeah, just not as good as with, yeah.
So I had sort of a related question on the voting. So you've got each of your individual model selections for 8 tools, okay, and there's a majority opinion as to what that is. Is there a logical equivalence of that to applying your shape signature algorithm to all of those 8, the data from those 8 tools smushed together? Would you achieve the the same conclusion?
Um,
Would you achieve the majority opinion by smushing all that data together and just figuring out
just
what
run the normal, the initial fit on that.
yeah, on
So the algorithm as it stands can't do that because it's breaking things up into tool, sensor, step.
sure. Yeah.
But if you were to not do tool, sensor, step, and just combine all the tools in a single prior for all the tools.
Then you have to have a prior and prior. Right? Because each tool has a different set point, so it has a
Right,
different
yeah.
name.
Yeah.
That's the problem with it.
You have
That's
to put a prior on the tools.
yeah, that's the fallacy.
That would be
Yeah.
a cool way to do it. It's probably
Yeah.
the right way.
Yeah, probably actually.
Well, okay.
Good enough, John.
Have you thought about like maybe like for example that one, like penalizing the amount of parameters, like so like just because like the damped one has like more parameters, so of course it's probably going to fit those better even if it's just like tiny amplitude oscillations, right? That's probably why you chose it, right? So have you thought about penalizing the voting based on like the amount of parameters?
No, I haven't penalized the voting based on that. Like as you know, the PIC penalizes it, but the voting is just doesn't
Okay.
count for number of parameters.
Oh, wait, I thought you said you went towards the most complex.
Yeah,
If
so-
if there was a tie, you went towards the most
Oh no,
complex.
yeah. If there's a tie, go to the most complex because it's for me it's the cost of the false positive cost is not as expensive. It's not as much as the false negative in this case.
Yeah, because you're probably getting just amplitudes that are like close to zero anyway, right?
Yeah, and
Yeah.
then if you learn like a constant model when it's oscillations, you miss losing a ton of information about how that feedback controller is behaving.
So when in doubt, throw in a parameter.
Not always. This is like one case where you don't like. I usually would want to, in general, err toward favoring the simpler model, the whole optimization thing. But in this particular application, I reasoned that it was the opposite.
Well, it's as simple as possible, but it's simple.
Yeah.
So it's not sufficient to explain all instances of it. Would I?
That's true. Yeah, simple as possible, but wasn't.
All right. Any other questions? Let's thank Andres. Thank you very much.